And I'm back. A whole day might have gone by for you between watching these videos. For me, it was like 2 seconds. Crazy. So we're going to start with number 4 here. This is part 2 of your third assignment from Unit 9. 50 kilogram cart is moving across a frictionless floor at I don't know why you would have to have a cart. Cart implies wheels, I think, and it's frictionless, so whatever. 2 meters per second. A 70 kilogram boy riding in the cart jumps off so that he hits the floor with 0 velocity. Okay? And then we're going to do all our stuff here. So this is a boy in a cart. They're together, and then they separate. That is what we're going to call an explosion. And the boy and the cart are together here, so I'm not going to make them as 2 separate things because they're together. And I imagine that they are moving in the positive direction. I'm going to choose 3 blocks here. And then they explode, separate. So let's see, and afterwards, the boy hits the floor with 0 velocity. So there's 0 there, which means the cart has to have all 3 of those blocks. All right. Momentum conservation equation here. We got the momentum of the boy plus the cart. On the other side is equal to the momentum of just the cart. Right? And how large an impulse did the boy give to the cart? Well, impulse is equal to change in momentum. So I feel like I want to do this first. Let's do this first. I'm going to do D first. So this is the mass of boy plus cart. That's 50 and 70. Maybe I'll write that out so you can see. All right, that's the cart and the boy together times velocity equals mass, this time of just the cart, times the cart's final velocity. So that's going to push some buttons on my calculator, 120 times 2, and divide it by 50. So that final velocity of the cart is equal to 4.8 meters per second. So there's 2 ways that you can do this. The impulse that the boy gives the cart and the impulse that the cart gives the boy, they're the same. The change in momentum of both of them has to be the same. So you could do the impulse of the boy, change in momentum of the boy. He has, that's the mass times change in velocity of the boy, which is mass of boy 70 times, he goes from having 2 meters per second of velocity to having none. Right, so I'm making that -2 because he went from having 2, if you wanted to write out the initial, final minus initial, be 0 minus 2, right? So that's negative 140 kilogram meters per second. So that means that what impulse does the boy give the cart? That means the cart, with the equal and opposite Newton's third law, the cart gets a boost. If the boy is losing 140, the cart must be gaining 140 because conservation of momentum. So that's the impulse. You could also do, what's the change in momentum of the cart? Well, that's the mass of the cart, which is 50, times the change in momentum of the cart. Final velocity, this is the version if you did D first, 4.8, and before the explosion it was going 2, and then you do some math and you're like, oh, I got 140. Yeah, because you better get the same thing. Physics. So just like Newton's third law, equal opposite force, if two things interact, there has to be equal and opposite impulse. So impulse on boy, negative 140, impulse on cart, positive 140. All right, two girls with masses of 50 and 70. What? 50 and 70? Boys and carts, two girls. Looks like 50 and 70 is the way to go. Are at rest on frictionless inline skates. It's like rollerblades. The taller girl pushes the shorter girl. I guess we are supposed to assume that this is the taller one and this is the shorter one. Maybe some unfair assumptions about body types there, but we'll let it go. Taller girl pushes the shorter girl so that the shorter girl rolls away at a speed of 10 meters per second. So this is, they're at rest at the start, and you can imagine they're like holding, like pushing their hands up against each other, and they're about to push off. So they're together at the start, and then they separate. That is an explosion. That's what we're going to call that. And since they're together at the start, this is the tall and short together, and they don't have any momentum because they're at rest. So that means our total over here is going to have to be 0, 2. So now they separate, and the shorter girl rolls away. If I kind of imagine her going in the positive direction, but you choose whichever direction you choose for the shorter one, taller one is going to have to go the opposite direction. Because I started with 0, so this has to total up to 0, positive 2 and negative 2, or 3 and 3, or whatever you chose. Okay, so momentum conservation equation, the momentum of the tall girl and the short girl together is going to equal to their separate momentums there. Calculate the impulse that each girl imparts to the other. Well, impulse equals change in momentum. So the impulse, which is equal to change in momentum of the short girl, is equal to her mass, which is 50. And her change in velocity, she ends up with a velocity of 10, started with a velocity of 0, so that's 500 kilogram meters per second. And that means the change in momentum, impulse of the tall girl must be negative 500 kilogram meters per second. And it would be very easy to then figure out, I feel like I should have asked you also, what's the final velocity, I'll put this in brackets because I didn't actually ask you to do this, what's the final velocity of the tall girl? Well, let's see, her change in momentum is negative 500, which must be equal to mass times change in velocity. Her mass is 70, and she's going from, I don't know what her final velocity is, but her initial velocity was 0, so her final velocity must be negative 7.1 meters per second or so. So didn't ask you for that, just asked you for those. Last one. A 2-kilogram melon is placed balanced on a circus performer's head. An archer shoots a 50-gram arrow at the melon with a speed of 30 meters per second. The arrow passes through the melon and comes out the other side, still going 18 meters per second. Yikes. I'll try this at home. This is a collision. The two objects are not starting together and then separating, so the objects are the melon and the arrow. To start with, the melon is just sitting there on the person's head. It has 0 momentum, and the arrow has all of the momentum. I'm going to make it 3 bars worth. So I think that'll be a good number to split up. And then afterwards, the melon is going to have some momentum because an arrow just ripped through it. And then the arrow still has about 2/3 of what it had before, so I think that's a decent picture. Important thing about the diagram is I have 3 positive bars here, so total 3 positive bars here. What does my momentum conservation equation look like? Well, I have the momentum of the arrow to start with has to equal the momentum of the melon plus the momentum of the arrow after. These are not the same P sub A. This is the initial, this is the final. Find the speed of the melon as it flies off the performer's head. So here, the momentum of the arrow is the mass of the arrow, 0.05. Grams are not the right units, kilograms are. So 0.05 times 30. Right, that's how fast the arrow is going at the start. And then on the other side, I have 0.05 times 18. That's the momentum of the arrow afterwards, plus the momentum of the melon. The only thing I don't know is how fast the melon's going after that arrow rips through it. I picture like a cantaloupe. I don't know what you're picturing here for melon. I don't think it's a watermelon. It's too small. Well, let's see, that's like a 4.5-pound melon. I guess it could be like one of those personal watermelons. But anyway, let's see how fast it's going. So I'm going to do some math. I'm going to find this and then subtract that. So 0.05 times 30 minus 0.05 times 18. And then I'm going to divide that by 2. So the final velocity of our melon here is a pretty sluggish 0.3 meters per second. So it's kind of like, I imagine it's like rolling off their head, right? Arrow ripped through it, kind of topples off the person's head. And that's it for this assignment.